Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Tell us about non-malleable stuff, non-malleable commitments, codes. It's really beautiful work. Actually, it's a culmination of a series of work that Tell has been doing. So welcome.
Thank you.
Also gets the award for the best dressed.
What about Nir? Yeah, thanks. Thank you, Vinod. Okay. Yeah, so I'm going to talk to you guys about 3-round non-malleable commitment from non-malleable codes. This is based on some joint works with Vipul Goyal, Omkant, Pandey, and Sunu Park. So we'll start with a commitment scheme. It's like a very simple two-party protocol between a committer C and a receiver R. And in the commit phase, the committer is going to send a string Z that's a commitment to his secret message M. And then in the decommit phase, he opens it. And the properties, security properties that you want are binding, which says that sort of no matter what string he sent in the commit phase, there's exactly one way to open it. And hiding, which says that sort of until he does decide to open it, just the string Z reveals no information to the receiver about what's inside, about the message. And there are different ways to formalize these exactly. What I've sort of written down is non-interactive, perfectly binding commitment, and you can build it from one-way permutations. Non-malleability is a security notion that goes back to Dolev, Dwork, and Nauer in 1991. And this is like an extra security property you could ask, and it concerns the setting where the adversary, he's a man in the middle. He sits inside two different executions of the protocol. So on the left, he's going to play as the receiver. He's going to receive a commitment to a message M. And on the right, he's going to have to produce. He's going to play as the committer. He's going to produce a commitment to a related message or to a message M tilde. And we say that he wins if he's able to generate a commitment to a related message. So for example, if M tilde equals M plus 1, then he's going to win. If this is an auction, he's going to win no matter what C bids. And so that's not good. And I'll also say that non-malleability isn't something that you'd expect to follow from just the hiding of the commitment scheme, because the adversary doesn't have to know what he's doing in order to perform this attack. He doesn't have to know what he's actually committing to necessarily in order to still maul the commitment. So okay, to formally define non-malleability, the intuition we want to keep in mind is that it's sort of infeasible for the man in the middle to produce a commitment on the right, M tilde, which depends on the commitment on the left. All right, and to formalize this notion, you're going to use, we use the real and ideal paradigm. The real world is exactly this, this picture. And the ideal world, it looks similar. It's pretty much similar, except that there's no left execution. There's no left protocol. Instead, there's just a simulator who always commits to 0. Okay, and we say that the protocol is non-malleable if the man in the middle can't tell which world he lives in, given his view and the value he's committing to. Okay, and so I'll just point out, surely this captures the intuition we want, right? Because if the man in the middle can't distinguish M tilde in the real world from M tilde in the ideal world, then certainly M tilde in the real world can't depend on M, right? Because in the ideal world, there is no M. There's just 0. Okay? So since 1991, numerous applications for non-malleable commitment have been found. Most notably to secure computation. In fact, in some settings, the only way we know how to get constant round multi-party computation is via constant round non-malleable commitment. And sort of any sort of composable two-party computation you could imagine would have to sort of be non-malleable. It would have to have some sort of non-malleability. So these are two prominent applications of non-malleable commitment, and numerous others have been also discovered since 91. So I mentioned sort of secure auctions. Also, you can, using non-malleable commitment, get a lot of other non-malleable primitives like zero knowledge or coin flipping. And then other applications also have been found. I list some here. Okay, so before I move on, I want to motivate a little bit further the definition of non-malleability. And I want to do so by arguing that it's really just the analog of semantic security, but against this active sort of adversarial channel. Okay, and if you think about it, semantic security considers the setting where the C wants to send a message to R, and the adversary is the channel, and he's going to eavesdrop on what they're sending. Okay, so this is sort of a semi-honest man in the middle who's just going to receive commitment or encryption or whatever, and he's just going to forward it. And we want the man in the middle can't sort of know what is on the channel. All right, and non-malleability is sort of the same idea, except now the adversary, like the channel, is hostile, and he can actually change the message, or overwrite the message, or just like not send the message. And so you're sort of like, at least Dolev, Dwork, and Naor, they were sort of asking what kind of security can we hope to achieve in this like much more hostile model. Okay, and so from this point of view, you can ask also the question, like, why did it take so long? So semantic security was in '82, and like 10 years later, only 10 years later, this like very natural generalization came up. Yeah.
So the man in the middle is not required to produce an opening. So eventually, the committer will open M, right?
Right.
And you could make the definition weaker, I suppose, by asking the man in the middle to also open.
Yeah. So actually, there are numerous like different variants of this definition, sort of mostly motivated by their applications. So they'll give a different definition and show that it also applies to to MPC. And so what you're talking about is called non-malleability with respect to decommitment, where the man in the middle is allowed to, he doesn't have to know what he's committing to, but he has to be able to open it if given the opening on the left. So here, it's even stronger. We're saying we're not even requiring him at all to open it. He sort of gets this like Oracle decryption or whatever query that they're just going to tell him what he commits to. Okay?
Commitments can be interactive.
Yeah. In fact, usually it will be interactive. I'll say more about like how many rounds and stuff. But yeah, so the ordinary commitments that we were using before, just the like perfectly binding non-interactive, those are non-interactive. But yeah, non-malleable will require some interaction. Okay, so sort of back to this question, why did it take so long? Like, what had to happen in between semantic security and non-malleability? And the answer is just. I'm asking why did it take so long to define non-malleability, or to why did it not appear until later? And I think the answer is that just the crypto in the early '80s wasn't really equipped to handle proving non-malleability. They didn't have the machinery involved. It really took like the development of zero knowledge, proofs of knowledge, non-interactive zero knowledge, in order to construct a scheme that you could prove was non-malleable. And this sort of, in 1991, Dolev, Dwork, and Naor came up with the really nice idea that, how do you prove non-malleability? Well, you force M to demonstrate knowledge of what he's committing to. Okay, so if you look at this picture, sort of the idea is that if man in the middle knows M tilde, then it can't depend on M, right? Because that's just hiding. So if he knows M tilde, then the hiding of the commitment scheme says that it can't depend on M, which is computationally hidden from him. Okay, and so Dolev, Dwork, and Naor say that if you want to prove non-malleability, you have to give an extractor that will extract M tilde. Okay, so sort of for this reason, all of the non-malleable commitment schemes in the literature, they look like this. They're really just fancy extractable commitment schemes. They're like more complicated versions, and you can throw some stuff in, but really it's like sort of a commitment at the beginning, and then a bunch of query, answer, and sort of you have to show that you can extract from the right. Okay, but there's like a catch. So normal extractable commitment, you just sort of rewind, you ask another query, you get another answer, and then you're like, okay, now we know what he was committing to, we've extracted. Okay, here it's different because there are two protocols, and so before he's going to give you an answer, he's going to ask a query of his own, and you don't know how to answer it, okay, because you don't have knowledge of M, right? We're trying to argue that the man in the middle knows what he's committing to independently of what's on the left, right? So if our extractor our extractor has to be able to extract M tilde without using knowledge of M. Okay, that's like really important to non-malleability. So what you have to do in order to build non-malleable commitment is you have to build an extractable commitment that's able to sort of extract even though you're answering with this like bogus query. Or you're answering this query on the left with this bogus response. Okay, does that make sense? So again, to prove non-malleability, we need to extract. And moreover, we need to extract from the right without using knowledge on the left. Okay, that's like the entire problem in a nutshell. And I'll show you prior work in a minute, but all the prior work on non-malleable commitment is really like more and more efficient solutions to this problem. Okay, and efficient in one way, I'm talking ground complexity. So maybe it's not like immediately obvious, but hopefully you could imagine at least that this problem gets easier to solve if you have more and more rounds with which to like ask a question and get an answer. Yeah.
Do we know that non-interactive, non-malleable commitment is impossible?
Yeah, so I'll say it in a sec. Yeah, there's a lower bound. Yeah.
Sorry, so how does the definition, I mean, you have to somehow have a syntactic requirement that
Yeah.
prevents copying, right? I mean,
Yeah, okay. So, yeah. Okay, so yeah, it goes back to DDN. It's sort of like not something I want to talk about too much, but the main idea is that, so ordinary non-malleability says the man in the middle can either copy, he can act as a channel, or he can do anything else, and if he does anything else, then he can't get something dependent. So sort of his behavior dichotomizes into like either he's copying, and so it's just like you can't, like that's not a valid attack, or he's doing anything else, and then it's like you can defend against it. And there are ways to sort of, you have this notion of like identities and stuff, and that comes out of this idea. So usually an identity is maybe like a verification key for a signature, and so you're gonna, in addition to committing with your own identity, you're gonna sign, and so now either he has to copy exactly, or he has to like forge a signature. So usually you build in the identity of the committer using this sort of, I don't know, using some additional stuff. But yeah, it's like, I would say just let's not worry about the copying man in the middle, because I mean he's semi-honest anyway, and that's like semantic security. So. Okay, so prior work is like more and more efficient in terms of rounds, solutions to this problem. So here's the prior work. 1991, w.r.t, amazing paper, define non-malleable commitment, along with like a lot of other stuff. And they give a protocol for it for with logarithmically many rounds. Yeah?
Do you have intuition why many rounds would help?
So yeah, it's just like you have more flexibility. So a lot of these schemes, they play games with like, the scheduling of the rounds like corresponds to this identity, and so you can like, as long as the identities are different, there will be 2 rounds on the right that sort of are.
It's really about how efficiently you encode identities into the scheduling. Or something.
Yeah, so that was DDN's idea. Like later, they sort of the identity corresponds to like the challenge space in like various parallel executions. So basically, you can parallelize this idea, but you just have to be a little more crafty. So, but still, like the number of rounds is like really important because you really need. I mean, sort of the premise is like if, well, I'll get into this later. I mean, it's really like, there's no like overarching answer to the question. It's just like in the literature, when you sit down and try to prove something, like it helps to have more rounds.
you're saying, suppose by some magic, right, the second and the third line on the left, right, the Q1 and A1,
Yeah.
was inside the second and the third line on the
Yeah,
left.
then you wouldn't have to rewind. You wouldn't have to do anything on the left. You'd just be able to extract. So that's one idea to do it, but that requires a lot of rounds. If you want to do like more, concise, you can sort of parallelize stuff. And this is this idea of like making the challenge space where this query comes from much, much larger than the challenge space where this query comes from. Because then the point is like, this answer can't possibly give him enough information to give this answer. That's like another idea. Yeah, so that's like the 2-slot trick, and then you can parallelize it again if you want. Yeah, lots of ideas in these like things, and I'll tell you about them in the prior work. So in DDN, yeah, this was the like logarithmically many rounds. They're doing the scheduling trick using the identity. Then about 10 years later, Barak and then again past Rosen give a constant round non-malleable commitment using collision resistant hash and non-black box simulation. This is like Barak's idea, and this was the 2-slot trick, the long short. And then again, a few years later, Rachel Lin and Raphael Pass, and also Vipul Goyal, give constant round non-malleable commitment from one-way functions. No, so no, there's some prior work that I think maybe Rachel and Raphael's is. I'm not positive, but Vipul's is not. Neither of them is. And then yeah, so there's a follow-up work with like Goyal. I'll say it in a sec. That gets they use MPC in the head instead of sort of the zero knowledge thing to get black box. A few years ago, Raphael Pass gives a lower bound. He shows that actually 3 rounds are required. You can't have non-interactive or even 2-round non-malleable commitment. So no, it's like you can't have a black box reduction to a falsifiable assumption. Yeah. Yeah, you can't base the non-malleability. Yeah. So random oracle or CRS, you have non-interactive solutions, so it's fine. Okay, so yeah, this is a plain model. So then a few years ago in this work with Vipul and Alon Rosen and Margarita Wald, we show how to get 4-round non-malleable commitment from one-way function. And this is like parallelizing everything as much as you can, and you have to do a bunch of work. I'll talk a bit about this because this will really be our starting point for the 3-round scheme. And there are like many more works, like by some people in this room also, that just, this is like a very well-studied area, lots of really nice results. So yeah, that's like a rich history here. Okay, so now I want to talk about the 4-round scheme to sort of give an idea of how these schemes work, what you have to prove, what you have to like intuit, and then we'll go from there to try to like see if we can shave off, go to 3 rounds. Okay, so this is not the scheme. This is like sort of the main subcomponent of the 4-round scheme from GRV. And the committer has a message M. It's a field element that he wants to commit to. So he chooses like a random other field element, and he commits to them both. He sends commitment to M and commitment to S. And then the query is just a field element, a random field element. Okay, and he responds with this like random, with this linear sort of evaluation, this linear form. It's A equals like the random value he committed to times alpha plus the message. And then he proves in zero knowledge that he answered correctly. M is the message, S is random. S is just some randomness, yeah. Okay, so again, this is like, I'll show you in a minute just to give an idea of sort of what types of attacks show up in non-malleable commitment. An attack, actually I'll show you right now. So there's an attack on this protocol. This is not non-malleable, but it's sort of like the main subcomponent of this scheme. I'll show you we'll talk a bit about it. So here's an attack, very easy attack. So yeah. Yeah, so it's certainly a commitment. It's hiding by the like zero knowledge. Yeah, so if you want, you can parallelize this. You can use the fact that zero knowledge, sometimes the theorem doesn't have to be known until the last message, and you can put it all into 4 rounds. Yeah, so yeah, you can parallelize this if you want. Okay, so an attack. So the man in the middle receives commitment to M, commitment to S, and he malls. This underlying commitment scheme is malleable, so he on the right produces commitment to M plus 1, and he just copies over commitment to S. Okay. Now he's asked for a query alpha tilde, so he like copies it, and he gets a response A, and then like what does he do? What's the answer? Yeah. Okay, and then he mulls your zero knowledge proof, no problem. Everything's malleable. And now he's done it. He's done this attack that we said in the first slide, where like he's gotten an attack to M, a commitment to M on the left, and he's produced on the right a commitment to M plus 1. Yeah, you're right. Thanks. Yeah, zero knowledge proof of knowledge, sure.
You can still mull it even though you don't know that A plus this is okay?
Yeah, it has no non-malleable guarantees, so like, why not? I mean, unless you want to assume it's a non-malleable, like it's not necessarily so easy for him to do that, but you can't rule it out unless you have some non-malleable guarantees on the zero knowledge.
Right. Maybe like commitment of knowledge would not be, it will necessarily be non-malleable, but zero knowledge proof of knowledge is not necessarily non-malleable.
I mean, I'm not sure that extraction is going to help you, because if you're really just extracting from yourself. Like you will whine, you ask him a query, he's going to ask you a query. Yeah. You answer. You need to sort of somehow get around that. Okay. Okay. Again, this is like the main building block of the scheme. So sort of I don't want to go too into it because it's not the point of this talk. But to prevent this attack, what we do is we sort of run n parallel executions of this mini component. And we vary the challenge space sizes in order to prevent this sort of direct attack. So what do I mean by that? Sort of like instead of drawing alpha tilde randomly from the field, you draw it randomly from a proper subset of the field. And now the idea is that if the size of the subset you're allowed to use here is much larger than the allowed size you're allowed to use here, he's not going to be able to do this sort of copying type attack where he takes your query and just copies it over. Yeah, it's not a subgroup. There are these fixed known subsets. If you want, you can do subgroup, but I don't think it helps. And then, yeah, so those are fixed. Those are public. And then, yeah, he just draws randomly from that subset. And the idea is that because using these identities, you can sort of vary the sizes in such a way so that there are going to be places on the right where the challenge space is much bigger than on the left. OK, so why am I telling you this? I'm sort of getting to one main idea. Sort of what you've done here is you've just blown up your protocol. Now it's much more complicated, and now there are maybe many more types of mauling that the adversary could do. Okay, so just because we've prevented this direct attack doesn't necessarily mean it's non-malleable. Okay, and so actually most of the work in GRV goes into proving this sort of independence lemma, which says that if you set up your sort of parallel executions properly, then there's no other behavior the man in the middle can do except to try to do this direct attack. Okay, and this sort of independence lemma we'll mention maybe at the end. Like it'll come up later. It's sort of used in some other ways in these 3-round schemes.
The n repetitions, you use different subsets probably, right?
Yeah, in each one, yeah.
The guarantee is that there exists a repetition where the right-hand side subset is larger.
Yeah. And so then the point becomes like, okay, so maybe there's one on the right that's larger, but maybe he's going to use like half of that subset for this one and the other half for this other thing, and then you show you can't do that. That's sort of, I don't know, like, yeah, that's most of the work. That's this independence lemma, basically. Okay. So now I want to talk, so there are like 2 sides of this non-malleable commitment coin. There's like the intuition, where you have to think about like whether your scheme is like, has these attacks, you know, whether there's like an actual explicit attack on your scheme. And then you also have to like, once you decide there isn't one, once you pass the sanity check, you have to actually prove, you have to build an extractor. Okay, you have to actually prove that your thing is non-malleable by constructing an extractor. Okay, so I want to show you the extractor here because sort of the extraction ideas also will be there in our 3-round scheme. So, okay, so how do you extract? So maybe is the thing you'd come up with if you thought for a little bit. The extractor is going to rewind, ask another query, alpha tilde prime. Okay, and then there's going to be a query alpha prime on the left, which he's going to answer just randomly. Okay, he doesn't know m, but no problem. He just sends a random answer, and the man in the middle can't tell because that would break hiding. So you send a random answer, and you get a response, a tilde prime on the right. Okay, now you sort of have 2 points and 2 unknowns. You can sort of solve the system and recover m tilde. You can extract. The problem is that you have no guarantee that a tilde prime is correct. Right? You have a zero-knowledge proof, which proves a tilde is correct. You have no guarantees a tilde prime is correct. Okay, so you might extract the wrong value. So no problem. This is like, this idea is used a lot in this extraction type of protocols. You just do it again, right? You ask another query, get another query, respond with random. Now you have like an over-constrained system. You have 3 equations, 2 unknowns. You check if it's consistent. And if it is, you deem that it's correct. Okay, so you have this sort of consistency check, which namely is, are the 3 points that I have consistent with the same 2 unknowns? Are they collinear?
You said it was used before, but it wasn't.
Not exactly. This collinearity idea was pretty like new and stuff, but yeah, the same.
The idea of rewinding, 2 rewindings.
Yeah, like you have to build a check-in somehow. Sometimes usually what you would do is add more rounds, and so you have some other thing that comes later to verify with, and that's sort of like easier, but you don't. So yeah, I guess one of the main ideas was you don't actually have to do that. You can use collinearity by rewinding twice and checking. That's fine. And you have to prove that this thing like actually works, but it does. It's no problem. Okay, and then this extractor is going to work with non-negligible probabilities. So you can amplify it many times if you want high probability, and this is the extractor. Yeah?
Larger than number of possible alphas.
So that's the independence lemma, to show sort of this independence lemma that there's nothing he can do except like maul them directly. That, yeah, you really need that's an independence lemma. So okay, good question. So how does the proof go? So the extractor is just sort of the starting point. Now you have to show that this extractor works. And so what you do is you like say, okay, suppose it doesn't work. Then that means that there's going to be sort of a man in the middle who isn't answering on the right correctly, even like when you're given randomness. All right, but he is answering on the right correctly when you're giving him correct answers. So he can sort of tell. And so you have to use such a man in the middle to break hiding. And you really have to get in there and sort of argue, like look at the ways he can actually maul. He can actually like, what are the ways that this query can depend on this query or this set of queries on this set of queries? And so that, like just all over the place, you're using the fact that these queries are like alternately large and small and stuff. Yeah?
If the consistency test fail,
Mm-hmm.
you have like a different reduction to hiding or something like that? What happens if it fails?
Okay, so you're asking what happens if he's never going to answer correctly on the right. He's only answering correctly on the right if you're giving him correct answers on the left. You give him random, he gives you random. So yeah, you have to use such a man in the middle to break hiding, and you have to go through a bunch of different types of cases. So you look, okay, so I don't, like this is getting into the GRV paper, not really what I talked about, but yeah, you have to like study the different ways these challenges can depend, or sorry, these challenges can depend on these challenges. And then you argue that sort of any way he wants to do it, to like line up these challenges with these challenges, he's not going to be able to because like the challenge space sizes over here are too different for him to use over here. And so then you get to the point where he's just breaking hiding. Like he's just answering you correctly if you give him correct, and incorrectly if you give him incorrect, and you can just break hiding.
The consistency test is just something in the proof.
I mean, no, the consistency test is, you need a consistency test somewhere in your extractor. And so what previous protocols did is they had more rounds, and you would just compare with like a later round. Yeah.
This is, so you said repeat something in parallel in times, right? So this is one instance of the
One
protocol,
instance, yeah.
and I see.
But the extractor, you're going to do it all at once. So you just do it all at once and see.
Of course.
Yeah. Okay, so I want to bring our attention here to a question. Okay, because this is really getting to like what's stopping us from just getting 3 rounds. So what's the role of zero knowledge here? Yeah. Yeah.
Cannot get better than 3 rounds under one-way function? What?
No, under any, okay, so it says if you have a protocol whose like non-malleability, you can think of that as like a reduction from an adversary who breaks non-malleability to an assumption.
Right.
If you have like such a setup and the reduction is black box, then it's not a hard assumption. You can just break the assumption.
So for under any falsifiable.
Any falsifiable assumption, yeah.
And under.
Sorry.
Yeah.
So I mean, your result is under one-way functions.
One-way permutations, because we need non-interactive commitment, yeah.
Sounds good. But
Maybe even actually one-to-one one-way functions or something. I don't know, whatever.
okay, but if you're willing to, let's say, rely on, collision resistant or even LWE, so what's known? I mean, how much is the
The lower bound applies.
Lower bound would apply for any falsifiable assumption.
There's like 4 messages. Is it easy under different assumptions?
I see. So we're sort of doing the like generic constructions here. So if you want to start from a commitment scheme, which you can build from like LWE, then you can get this. Like we're not going through LWE. I'm not sure that there's any benefit.
Not necessarily to you,
Yeah.
I guess. It's just.
Was there an easier construction?
I get, all these construction of non-malleable commitments are very complex. You're like,
Yeah,
doing
yeah.
all this thing. I'm just asking, is all this complicated thing, is it to get like this holy grail of one-way function? Or like under LWE or something? Or is it very easy?
I see. No, so I don't know that you're going to be able to do much better. Like from DDH, for example, you can do some of this stuff that's like a little bit faster using these like Schnorr type of protocols. But I don't think that you could get 3 rounds even. Like at the end of the day, you have to extract, right? And so you have to be able to prove that when you answer with randomness here, he's going to answer with randomness here. And I think sort of there wasn't really a way to do that before without using zero knowledge. Like if you're not using zero knowledge.
This work, there was no 4-round non-malleable commitment from any falsifiable assumption.
Yeah, from the before. Oh, yeah. Except for like in the plain model, like CRS, you could do it. Yeah. That's true.
The first.
Yeah.
With the w.r.t protocol, in terms of like black box reduction, would it be covered by Raphael's lower bound, or I mean, number of
so his black box, his reduction. So okay, there's like 2. Like one is the proof of security, which uses the non-black box proof of the. Sorry, non-black box use of. Yeah, so I'm not sure that his would be covered by the Raphael's thing. If you want to use the crypto primitive in the non-black box way, that won't help you. But if you want to use the adversary in the non-black box way, I think that might get around this. Yeah.
So you're saying there could still be a 3-round non-malleable commitment
2-round.
where you, 2-round non-malleable commitment
Yeah.
where you use the adversary as a
Yeah.
black box.
Yeah.
But if the adversary computes like the one-way function,
That's
then you can't even use the adversary in non-black box. 'Cause then wouldn't you be using the one-way function non-black box?
fine. And that's another way to. I mean, non-black box and everything. Is one way
Yeah.
to-
And if you want to do it, if you want to do it, it's. I'm not sure this intuition is sound because I haven't really thought about that direction too much. But it seems to me like really it's an issue of extraction. So a lot of these sort of other problems that maybe are hard, like I don't know, extractable zero knowledge in under 4 rounds or something. You might need to look at those and show how you can like extract even though you don't have something to rewind and then use. So it's like it seems like that's sort of the issue that you need to get around. Okay. Okay. So question: what's the role of zero knowledge here? So how important is zero knowledge? Right. You need 4 rounds for like zero knowledge most of the time if you want to have a black box proof of security. So if you want to get 3-round non-malleable commitment, you can't use zero knowledge. Okay, so how important is zero knowledge here? So in particular, so what is zero knowledge doing here? It's just proving correctness of a tilde. And that's like allowing your extraction to succeed. But my question is like, how important is that? So what? So maybe you have an extractor that will sometimes extract the wrong value. Is that really like, is there an explicit attack on this scheme if you remove the zero knowledge? So like this scheme. Okay? So I want to show you an attack. This was sort of the starting point for 3-round non-malleable equipment. And there's like an explicit, very easy attack. And I think it represents a lot of the struggle for 3-round non-malleable commitment. OK, different attack than we saw before. So what does the middle do? He receives a commitment to M, commitment to S, and he produces on the right a commitment to M tilde, and he copies the commitment to M over to where the commitment to S tilde should be. OK, and then he's asked a query on the right, and he just ignores the left. And he answers with 5 times alpha tilde plus M tilde. OK, so what has he done? He's basically just guessed that M equals 5. And if M equals 5, he's produced a valid commitment to M tilde. If M equals not 5, then he's bought. OK, and so this attack is like pretty explicit. It's not something that you want, right? Especially if like the message space is going to be small. This would be like really bad. And it's also like no amount of this parallel repetition is going to like ever prevent this attack.
Sorry, wait. So it completely ignores the message.
Yeah. Yeah. OK, and this attack, so it's sort of more general. Like you can like phrase it this way. It's real simple, but it's actually a general sort of attack. It's going to be possible anytime the man in the middle's message is specified, fully specified after the first round, right? Because you don't have to just copy over the message. You can, like any sort of function you want to compute inside the commitment, you can't rule out unless you're assuming non-malleability. So if the commitment is defined, even information theoretically, in the first message, then he can just like compute it and then put it inside the commitment and guess that that commitment equals like 5 and the same attack. Okay? Okay, so like what's the point? So the point is that zero knowledge rules this out. These are called selective bot attacks, and these are the attacks, the hardest ones to stop in 3-round non-malleable equipment. And just sort of to like underscore the role of zero knowledge completely rules out this attack because it makes sort of the condition of whether or not the man in the middle is committing to bot or committing to valid efficiently verifiable, efficiently testable. Okay, and so in particular, whether he's committing to bot or not, it can't depend on M, right? Because that would break hiding. Because you could just verify his proof, and if this bot or not bot depends on his message, then you're going to break hiding. Okay, and so as a result, these attacks are completely not addressed in the non-malleable equipment literature because you're always having more than 4 rounds. So you always have zero knowledge, so it's no problem. You don't have to deal with these attacks.
So if you had a 3-message zero knowledge, you would add with nice properties, right?
Yeah, I think if you have 3 rounds zero knowledge, then you could just use zero knowledge, yeah. And sort of the fun, so people like 3-round non-malleable commitment because it's like a concrete thing. For me, sort of the fun part of this like project is doing it without zero knowledge. Because like, I don't know, zero knowledge is often the most computationally expensive and whatever, and like it's not clear that you need it, but it's like pretty useful. So getting getting non-malleable equipment at all without zero knowledge is like, this was sort of the first time. Okay, so yeah, the point, if you have more than 4 rounds, just use zero knowledge, which is why no one considered it before. But if you want 3 rounds, you have to do it. You have to deal with these attacks because you don't have zero knowledge. At least you don't have like the sort of black box zero knowledge that we're all used to. Okay, so for the rest of this talk, I'm going to talk about how to get around this problem. 3-round non-malleable commitment, and we're going to use non-malleable codes, sort of not in place of, but like I guess instead of or whatever zero knowledge. Yeah, because sort of black box just means like you're proving stuff about these crypto gadgets in the zero knowledge. And if you don't have zero knowledge, then yeah, it's black box. Which means more efficient, I suppose. OK, non-malleable codes. Really nice, really recent primitives from a paper in 2010 with Zimbowski, Pierczyk, and Wicks. What are they? So, numerous ways. Well, I've heard different people define them different ways. I like to think about them, I guess, as just generalizations of error-correcting codes. But sort of you have to look at error-correcting codes in the right way. So what do I mean? So anytime you have a code and you have some sort of tampering that you're trying to defend against, you can consider the tampering experiment. Namely, where like you take your message. This is going to be specified by a message and the tampering function. You're going to take your message. You're going to encode it to C. You're going to tamper it to C tilde, which is just f of C. And then you decode it to M tilde. And then you output M tilde. Okay, and sort of like, you can think of like different types of codes as just being like different requirements on the output of this distribution. And if you want to talk about error-correcting codes, then the tampering functions you're worried about, like the code words are just like, I guess, vectors. And the tampering that you're worried about is when you can sort of arbitrarily change a small fraction of the code words, or of the symbols. In error-correcting codes, you're requiring that M tilde equals M. Like you're actually correcting the errors. Okay, non-malleable codes are sort of, it's like a trade-off. They're saying, okay, we're willing to not exactly correct errors, but we want to be able to deal with much more like hostile types of tampering. Okay, and so they look at the same tampering experiment, and their intuitive requirement is just that either f is copying, in which case you have m tilde equals m. So like if f does nothing, or if f does like really simple things that don't change anything, then m tilde equals m. Or otherwise, m tilde is independent of m, sort of classic non-malleable style. Okay, so to formally define this, you say that a code is epsilon non-malleable against a particular tampering distribution if, sort of for all messages and functions from that family, the tamper distribution, which is that sort of distribution experiment on the top, is simulatable. So what do I mean by simulatable? I mean it's simulatable without the knowledge of the message. So there exists a distribution S that depends only on the function, and it's a distribution on m or same. Okay, so this is going to output like m tilde, or it's going to output same in the case when the function is not doing anything. Okay, you want there to exist a distribution such that for all m, the statistical distance between the tamper distribution and the sort of induced simulated distribution is less than epsilon, where the induced simulated distribution is just draw m tilde from the simulated distribution, and if it's same, output m. Okay, so it looks a little nasty, but it's really intuitive, I think, and it makes a lot of sense. It's saying, okay, either you're copying or you're doing something independent. Okay, so if you're copying, then your simulated distribution is going to output same. Okay, so if you're copying, this like induced distribution is just going to take the same and put it to m. That means you're copying this m. Okay, or otherwise, if you're not outputting same, then it was sort of simulatable without knowledge of the message, so it doesn't depend on your message. Yeah, exactly, for every message.
Distribution?
What?
Is it for every function f? Oh.
Yeah, so the simulator is going to depend on the function. So it's a new distribution for each one. And the point is that it simulates all of these tampering distributions, like for every f, the whole family of tampering distributions as m varies. Okay. Anyway, so there are lots of work on non-malleable codes. Many, in particular, many different sort of families of tamper functions have been considered. In this work, we're going to use the split-state non-malleable codes. And this is the one where the tampering function are split-state functions. Namely, sort of you encode your message m into two states, L and R. And then you can tamper those two states with functions f and g. You can tamper them however you want, as long as f and g act independently on the states. Okay, and this is like a strong sort of type of non-malleable code. Lots of recent work, really exciting recent work, has been done on this particular model of tampering functions. And yeah, so and these proofs are difficult. So using them is sort of like using a big hammer. So it's not if you want a like big result, you might have to use a big hammer somewhere. This is sort of a big hammer that we're using, I think.
Combinatorial hammer is supposed to operate.
Yeah, it's definitely like information theoretic. These are not crypto, yeah. Okay. Okay, so in particular, we're going to use the split-state non-malleable code of Agarwal, Dotis, and Lovett from a couple years ago. And so I want to spend a slide talking about it for a little bit. So the code is sort of splits. It's like two different components. There's the main component, which is really just the inner product. So if you want to encode a field element m, you pick like two vectors whose inner product is m, and that's L and R. That's your code word. And so then if you want to decode, it's just the inner product. Okay, so this is not non-malleable. I don't want to say that this is non-malleable. In particular, you can mall it pretty easily with some linear functions, f and g. However, it has like pretty strong non-malleable properties. And this is what they show. They show basically that sort of if you want to mall this code with f and g aren't linear, then you're not going to get, then you're just going to get random. It's just going to be independent of your message, essentially. Okay, so basically the inner product code sort of reduces to the case when f and g are linear functions, and then the second component is this affine evasive component, which protects against linear f and g. And I'm not going to talk about the second component. The reason we're using this code is because it's sort of so simple. It's just the inner product. I mean, it's not simple to analyze, but it's just the inner product. It's really sort of like, I guess, amenable to like the various manipulations and strengthenings that we needed. So it's not clear that our like work needs to use this ADL code. It might work. It could probably be made to work on sort of the more recent and more complicated ones. but I'm not sure. We haven't looked at it, and yeah, it might just be better to wait till like someone figures out like a someone improves all these more complicated ones with like a less complicated one, and then to use that. Yeah.
Any class?
Yeah, it can protect against split state. It's a non-malleable split state code, so it can protect against any like tampering function f and g that acts independently on the states.
And f and g are not computationally bounded.
No, all information theoretic. Yeah. Okay. So, okay, we've done all the like building. Now I'm going to show you a 5-round non-malleable commitment using non-malleable codes. This is going to like, I think, get to the point of maybe half of the ideas required to do 3-round, and then I'll show you 3-round. Yeah.
Even if you stay in 5-round,
Mhm.
there might be improvement in the actual implementation, right? Because the
Yeah.
they have this.
Yeah, in particular, like previous non-malleable equipment really needed to like amplify. They had many different parallel things, and they had to amplify sort of. They had to prove many different parallel executions of the same thing, and we don't need that. So this 5-round scheme, although it's actually not non-malleable, I'll tell you why. It's sort of a cheat, but I'm just like we'll deal with all the issues. But this scheme you wouldn't want to implement and like use for MPC because. In particular, there are scheduling issues. If the man in the middle chooses to schedule the messages differently than just the synchronizing one where he plays left, right, right, left, left, right, then you'll be in trouble with this scheme. This is non-malleable against synchronizing adversaries. It's not non-malleable against like non-synchronizing. Okay, so sort of the high-level plan, what we're going to do, we're going to do this protocol, which is non-malleable against synchronizing. We're going to shorten it to 3 rounds, still non-malleable against synchronizing, and then we'll give you a full non-malleable commitment scheme. 3 rounds. Okay. So let enc.dec be a split-state non-malleable code. We'll actually need some more properties from it, but we'll see what those are. They arise sort of naturally, so I won't tell you now what they are. Okay, and the scheme, yeah, we will construct what we need by building on this ADL code. The scheme looks like this. It's, the committer has a message M. He wants to commit to it. He encodes it. He gets L and R. He realizes L is a field element, just like, embedding it in some field. And then he draws another random element to that field, and he commits to them both. Okay, and then there's like this query. There's this response. Okay, then there's this acknowledgement message that I received your response. Yeah? Yeah. L is a vector over ZP, so we're just going to realize that whole vector space has another inside some other field. We acknowledge the receipt of this response, and then we send R. Okay, and just sort of whenever you see ACK messages in like a commitment protocol, they're cheating in this way. This ACK is explicitly to make sure that the man in the middle has to send his response A tilde before he receives R on the left. And so in particular, like he can break this with scheduling. If he wants to schedule the left to come before, he can break this thing. Okay? So this is like a cheat, but still, yeah. So okay, the tags are used because your message M here is actually your commitment concatenated with your identity. But you don't need to go to tags at all. You just have an identity, which is like a verification key. Yeah.
So L and R are generated by using the non-malleable code.
Yeah.
And then this L ZQ, what is that?
Yeah, so L, we're just taking this string or vector or whatever, and we're just like realizing it by embedding it into some field. Not algebraic at all. It's just viewing it as a field element. And then we like secret share it. We draw another element of the field, and we release one polynomial evaluation, like one linear evaluation. Yeah, so, OK, good. OK, so how do we prove that this is non-malleable? So, OK, so, yeah.
Ask you a question that I don't understand about this book in general.
Yeah.
So you're saying why is it so hard to do get non-malleability? Is because you can take your alpha query that you got and you can forward it.
That's one attack.
On the left.
Yeah.
That's one attack. But you can assume that the alpha queries that you allow depend on the first message. So you can't just forward alpha. It's not the person like you. I mean.
Wait. So you want to do this like, you want to make it non-interactive by having the query alpha depend on the first message and put them all parallel?
Even I don't mind that though it's going to be interactive, but I'm not going to allow you to. Not every alpha is admissible, and the alphas that are admissible depend on the first message.
But the first message here is a commitment, so.
Right. So,
Hash it or something.
yeah.
So that is a lot of times what you do, actually.
Oh, is it?
well, yeah, so another way to generate these identities is just a hash of the first message. If your message is defined there, then that's your identity. But I'm not sure I understand your problem, your question. So
I guess I'm trying. I guess I'm saying, doesn't it get around all your like these forwarding tasks?
So the problem with what you're trying to do, I think, is that if you restrict the challenge space, then you run into soundness issues, where the man in the middle can just abort, or he can like choose a commitment and abort if the challenge space would be like not to his liking, and so there's not enough flexibility for the honest receiver, and so you might run into like sort of attacks like that. Yeah, but I'm not exactly sure what you're proposing, so I'm not sure like how to. Yeah. Okay, so this is the scheme. It's non-malleable. So what's our plan? How we prove this, right? We have, yeah.
The first scheme that the commitment is not determined in the first message.
Oh, I don't know if it's the first such scheme. I think it might not be. I think sort of it's equivalent if you want to just commit to some randomness and then use that randomness to commit to your message at the end, it's probably fine. But yeah, notice that our message is not defined in the first message, in particular because of that attack where you can guess. Okay, so I claim that this is synchronizing. Sorry, any synchronizing man in the middle who models the commitment scheme can be used to break the non-malleability of the code. Okay, so what's our plan? How are we going to prove it? So recall previously we had to extract. We had to extract from the right without using any knowledge of M on the left. Okay, and such an extractor was really a reduction to hiding. Because what we're saying is, like, if we can extract the man in the middle's message, then he can't distinguish the real and ideal world without breaking, right? Because if he's given a view from either the real world where he's got a commitment to M, ideal world where he's got a commitment to 0, he can just extract his message and then use the non-malleability distinguisher to break hiding. Yeah.
I don't need to know the message until the very, very last round.
Yeah, in particular, right. So this sort of selective, like looking ahead a bit, the selective bot attack idea where he's going to like answer incorrectly sometimes based on some other stuff that we're not sure how to like analyze, it's not going to apply here. Because if he answers incorrectly, he's just committing to bot independent of what the message is on the left. Yeah.
Explain a bit more slowly why the selective bot attack you showed us earlier doesn't work.
Yeah, so like let's say, right, he wants to commit. I mean, he has a decision here. Does he send the right answer or the wrong answer? So let's say he sends the wrong answer. It's not like that's fine, but it's not going to depend on what your commitment is here because it hasn't even been defined yet.
Does it depend on the message?
Yeah, the message, your commitment message, your M. I took it out, but the M that you encoded with this L.
Something partially depend on the L, and it has to send the R tilde in a different way to depend on the R, so that when the L and the R determines M, the L tilde and the R tilde.
Wait, I don't understand.
I agree that he cannot do whatever you said earlier, which is
If you stop at that point. Yeah.
Yeah. But
So-
then maybe he's selective when he's doing the selective abort. He needs to choose L tilde and R tilde. Somehow he can wait to implement the attack until the R tilde. Right?
Okay, so I think not, because here's what you can argue. This is sort of how getting into the argument. You say, okay, suppose like we're looking at what's the chance that the man in the middle answers correctly here, and we say, okay, suppose it's small. Suppose he doesn't answer correctly, then like he's not mauling you because he's just always committing to bot. Sort of you play. Let me move on. I'll sort of maybe it'll become a little bit more clear. But yeah, I want to talk high level of how we're going to prove it, and then I'll show you how we're going to prove it, and then maybe it will become clear at that point. So okay. Recall previously you had to extract on the right without using information, your knowledge of the left, M on the left. Okay, here we're doing a different plan, right? We're using non-malleable codes. So what we're going to do is we're going to build two extractors, an F and a G. Okay, and then sort of we're going to have to argue that this F and this G together are going to extract L tilde and R tilde, which determines his message. Okay, and the benefit of doing this is that F is allowed to use L, right, on the left, and G is allowed to use R. You're just not allowed to use them both. Okay, so that's the benefit of using non-malleable codes, is you get to break your extractor into half, sort of. And you use half of the extractor, which has half of the information from the left, and the other half of the extractor has the other half of the information from the left. And as long as sort of you can keep everything straight, it's going to be, you're going to basically be able to reduce a man in the middle who mauls to tampering functions that break your code. Yeah?
From the adversary is constructed from the extractor.
your tampering functions are the extractor, basically. And they're going to run the man in the middle as like a subprotocol.
So the F and G here actually will depend on the adversary, though.
Yeah, they're going to run the adversary. Okay, so how do we define F and G? Sorry. How do we define F and G? Well, they're extractors, right? They have to sort of get some transcript and then rewind and extract. So they're going to get this first bit of the transcript. Okay, and then, then F is going to rewind. He's going to send another query. He's going to answer his query on the left, and then he's going to get another query on the right. Notice he's actually able now to answer on the left because he knows L. And he knows this like first query, the blue alpha A. So using so here, I say it here. Sort of using the point he gets as input in his blue transcript and his knowledge of L, he's able to actually answer correctly. And so you don't have to go through this whole exhausting work of arguing that even if you answer incorrectly on the left, he's still going to answer correctly on the right, because you can just answer correctly on the left using L.
So the guy, he knows L, he commits to L correctly, he picks an S at random, blah, blah.
No, so he receives, the F receives as input, sort of as randomness, this tau. And then he just goes back, and instead of sending this message, he sends green alpha tilde prime, and he runs the man in the middle to receive an alpha prime. He answers, he runs the man in the middle to receive this. And now he sort of has 2 points, 2 unknowns, he extracts L tilde. I didn't write that, but that's there, I think. Yeah.
That F and G are completely independent functions, right? F is
Yes.
a function that depends
Good.
on L. G is
Yeah.
a function that depends on L. Here they're
Right.
sharing something that actually depends on L.
Yeah, exactly. So G is actually going to get as input this transcript, which actually has a commitment to L in it.
Even F also has a commitment to L to it. But
Yeah, that's true. F's allowed to have L, so that's maybe a little bit more non-offensive or something.
Define it as though F creates this commitment. Why does
Okay. Because G isn't allowed to get that commitment. You have to force F and G to extract from the same transcript. You can't have F extract from this one and G extract from this one and then hope to argue that somehow you got lucky and they're going to put together to be the actual man in the middle's commitment. Right? We want to use the man in the middle who mauls this commitment scheme to argue that F and G are going to actually maul this code. You can't do that unless they're extracting from the same transcript. Yeah.
Is that a commitment to L or just some bogus 0?
No, so right now, it's a commitment to L and to S, and it's also this message. So it's the whole first line, and it has actually L inside of it. And what we're getting ready to do, right, is because F and G both are just going to receive this tau from the outside, what we're getting ready to do is we're going to say, okay, number one, if it receives this honest tau, in this way, it's going to actually maul your code. Not a contradiction because it's not split state, but then it's going to be indistinguishable from actual split state, and so therefore it must still maul.
Okay.
Okay, so G is really easy, right? It just sends R, receives R tilde. It goes sort of further down and extracts from the second half. Okay, and
You're saying I know alpha and A, and I can compute. Okay, good, because I know L. I can compute this correctly.
Yeah. Okay, so I guess the point is, right, that, so this is how you define F and G. You have to now prove non-malleability. And there are going to be 3 different steps, and they're sort of the same 3 steps. We'll use them again if we have time. Unclear. Okay, that's the claim, and these are the 3 steps. Okay, the first step is you have to argue that that if the man in the middle mauls, then these F and G are going to extract correctly. Okay, and this is getting to what Hotek was saying, where if he's mauling, I claim if he's mauling, he has to be answering A tilde correctly. Because if he's not, if you just get a transcript tau that has a bogus A tilde here, then because your message hasn't even been defined, it's going to be a commitment to bot no matter what message you later decide to commit to.
What do you mean by correctly?
I mean that A tilde is actually equal to alpha tilde S tilde plus L tilde. Right, that's what we were proving in zero knowledge before. So that's sort of the main difficulty, is arguing that even though we're not proving in zero knowledge that it's correct, we're not worried about the situation where it's incorrect. Okay, and that's just because the message hasn't even been defined yet. Okay, so step 1, argue that F and G are extracting correctly. Okay, and so so I'm sort of claiming here that if the man in the middle is mauling, then he's answering correctly, at least with some non-negligible probability, because otherwise he's just with high probability committing to bot, independent of the message.
correctly and A tilde prime.
Okay.
Something.
Yeah, so what you can
Why is he
argue,
committing to bot?
because, okay, so what you actually show is that, like, so if he's answering A tilde correctly, then it's really unlikely that he's like, that it was like really lucky and that every other query he's answering incorrectly. So you use this like Bayesian argument to say that if he's answering A tilde correctly, then with non-negligible probability, he'll answer A tilde prime correctly. So this is with non-negligible probability. This is not like, I'm not claiming that he's always doing this. Yeah.
Can I think of this as, I mean, it's interesting only if the adversary gives with non-negligible probability the correct A tilde. Otherwise, there is
Otherwise, it's bot, independent of your message. He's not mauling.
Oh, independent of.
No, well, otherwise he can't open. It's really
No, but he's committing to bot. Yeah, he can't open, but he's.
committing to bot.
So this is a perfectly binding commitment scheme. The commitment is going to be bot if he answered incorrectly. So like, what would he be committing to? What is he committing to? What's his commitment? So it's either like L tilde decoded L tilde and R tilde, or it's just bot if he answered wrong.
Right, so he can't open.
Not only can he not open, if he does open, he's going to get bot. Like we don't need him to open.
I guess what I'm misunderstanding is the guy on the right.
Yeah.
When he receives an incorrect A tilde and A prime tilde,
Yeah.
he doesn't already know that it's bot.
Yeah, but it doesn't matter. Sort of all we need is that with non-negligible probability, it's not bot. He got correct.
You can't at this point detect that it's bot. It's just
Right.
that in the future, he'll never be able to open it
Yeah.
to something other than bot.
Exactly. And so the point is that like the probability we're talking about, non-negligible, is over tau. So it's over the functions. And with non-malleable codes, you only need to show there exists one function. And we're sort of showing that, oh, there's actually a non-negligible fraction of functions that it's going to do. Okay, so step 2 is you have to use an M who's mauling. So F and G extract correctly, meaning they actually extract his message. You now have to use the man in the middle who's mauling to argue that F and G are mauling. And this is like not so easy, but you can do it. I'll talk about it on the next slide. And then the last part is this hybrid argument to get from this non-split state F and G, which maul your code, indistinguishably to this F prime and G prime, which are split state, and then still by the hiding will still maul your code. And this uses just the hiding, the fact that like L is computationally hidden in tau.
So you can just, in the third step, you just make com0, com.
Yeah.
You still need to check that F and G are completely independent, right? That seems somewhat non-trivial to argue because sort of G follows sequentially from F.
Well, I'm defining G in this way. Wait, I don't understand. What do you mean?
To argue, to use non-malleability of the code, you need to make sure that F and G behaves independently.
Yeah, so okay, so that gets into bullet number 2. We're not actually reducing it to the non-malleability, to like normal non-malleability. We need some like alternate type of non-malleability, which we build on top of this ADL thing. And it's exactly this issue that you're talking about.
Okay, so it's slightly, they don't have to be, they are only partially independent in some sense.
Yeah, okay. So this is trying to prove non-malleability, going from a man in the middle who mauls to a like tampering functions with maul. Okay, we would hope that sort of an M who is mauling, right? That implies there's this distinguisher that we can distinguish this real world and this ideal world. We would hope that this would just immediately give us like a distinguisher D prime, which would distinguish the tampering distribution with N from the tampering distribution with M prime. Okay, that's what we would hope. It doesn't quite work. In particular, it just like when you sort of unwrap everything from what this like man in the middle who's mauling gives you, it just doesn't give you the tampering distribution. It's not what you get. So what we have to do is define this sort of alternative. It's called conditional augmented tampering distribution. And this is building on top of augmented tampering distribution, which was defined in another work, to sort of show that like it's just a different tampering distribution, so it's a different definition of non-malleable code. Okay, and so I'm going to write down the tampering distribution, but I don't want to talk too much about it, just because it's a little technical and it's maybe not so interesting, but I'm happy. Well, anyway. Okay, so this tampering distribution is going to be specified by a message M, a function, and also a left state. Okay, and the way this works is first you draw R. So you draw you're sort of given this left state, and you draw an encoding R that's going to encode your message M given this left state that you already picked that was sort of drawn along with the functions. And this HOTEC is what you're talking about. You need, so L, because it was sort of, it's included in this tau. It's actually chosen at the same time as you're defining your functions. Normal non-malleability, L is chosen honestly here. For us, it's always the same L that's being chosen and a fresh R is drawn. Because L is chosen at the same time that the functions are defined. Okay, so yeah, you encode, and then you tamper, and then you decode, and you output. Okay, but you also output your write state. Okay. So, okay, note the differences. Two differences. One is that you're outputting actually the right state and not just the message M tilde. And this is because the man in the middle gets to see R. R is like perfectly open to him and is part of the view. Right? So the man in the middle and then the distinguisher is going to be able to make his decision not just based on M tilde, but also based on R. The other difference is that L is fixed once and for all. That's what I was saying. Okay, so this is like a different notion of non-malleable code. Yeah, and again, that's because L is chosen, it's specified in tau. So it's chosen along with F and G. It's not drawn naturally, sort of freshly in each execution of the tamper distribution. Okay, and so that's the conditional augmented tamper distribution. The definition, you say it's conditional augmented non-malleable if sort of for all of the stuff that you're given, namely message, tampering function, and this left state, this sort of new tampering distribution up here is going to be simulatable. Okay, and we have to, sort of statistical distance isn't the notion that we want anymore. We have to use like no distinguisher can tell like with high probability over L. So L is chosen sort of independently from this distinguisher, and we want these to not be the same. So anyway, I guess the point is that sort of we need this alternate notion of non-malleable codes because it's really just sort of what comes from a non-malleable committer who walls. Okay, and then you can build these using just sort of existing statistical arguments from this ADL code because it's so simple. It's really just the inner product. And so in particular, the augmented part, which is the outputting of R along with the message, that was already cited in this recent work at TCC. And then this conditional on top of it is sort of new to our work, but it's sort of like an existing argument. That was in the two-source extractor literature. It's not so hard. Yeah. OK. So I'm sort of getting to the end. So really quickly, 3-round non-malleable commitment. So all we do is we squash. We like get rid of this acknowledgement message, and we put the R alongside the answer A. Okay, and this is going to pose like a different set of problems. We have all the old problems from the 5-round scheme, and we also have the new problem, which this poses, which is the following, right? We have this extractor idea that we want to extract. We want to use F. We want to rewind, send a new query. Yeah, so we want to use F. We want to rewind, send a new query. But then in order to like send an answer here, we also have to send R, and F isn't allowed to know R. Okay, so this seems like we're stuck. Like it seems like it's not going to work. So the idea is you give sort of in addition to this like partial transcript, you give like a random value of R to send. That's sort of just a bogus value. So they share this bogus transcript, and then F is going to extract from this bogus transcript. G is going to extract from the normal transcript, but sort of check consistency with the bogus transcript. Okay, and sort of this idea, you have to do some work. In particular, there's a new property that you have to put into the non-malleable code, and it's not so hard. So yeah, maybe I'll just sort of run to that new property that we need, because I'm out of time. So okay, so here I'm just defining F and G like we did before. F works exactly the same, right? Except it's going to extract using this sort of bogus R tilde that it has. G is going to, it's just going to send A, the A that it receives in the transcript, along with the real value of R. It's going to get some A tilde, R tilde on the right, and it's going to check that sort of this is the consistency check we're talking about. It has to check that the A tilde it gets on the right is the same as the A tilde you got on the right when you sent the bogus R. Okay, and that's just to enforce that the like transcript which F is extracting from is sort of like equivalent to the transcript which G is extracting from. Okay, and right, to prove non-malleability, you need the same 3 steps. Right, 2 and 3 are exactly the same as this 5-round scheme. And 1 now, you have to show sort of the correctness of extraction piece of it, is you have to show that sort of the chance that A tilde is correct, this blue A tilde is correct, given that you answered using this bogus value of r, is the same as if you answered with this real r. Okay, so I'm going to skip through most of this. Let me see. Yeah, okay. So it comes down to this extra property of this code. It's like a semantic security type property on the write state. So what you want is that for any two messages, and with high probability over L, like the write state coming from an encoding of M0 given that L is like computationally indistinguishable from a write state coming from an encoding of the other message with the same L. Okay, and this, yeah?
Primitive, how do you end up with
So we have to use, so we're going to take the AGL scheme and we're going to build on top of it. Really, we're just going to put some cryptography on the right-hand side, and that's going to now satisfy this notion.
I see.
Okay, so the way you do it, like we say, sort of you just, you draw a key. So okay, you're putting cryptography on the right-hand side. Okay, so you have sort of ENC0, DEC0 is this information theoretic, conditionally augmented non-malleable code. And now you're going to build on top of it this new non-malleable code. What's it going to do? Well, it's going to, like if it wants to encode M, it's going to draw this encoding from the information theoretic version. It's also going to draw a key from a like symmetric key encryption scheme. And it's just going to, it draws some randomness too for a commitment. And then it's going to set L to be L0 that you got, the key, and this randomness that you drew. And on the right-hand side, you just encrypt your message, your write state, and you commit to the key. The commitment to the key is like sort of just so we can prove it. Again, getting back to this like intuition versus like actual things you can prove. It's sometimes not so easy to like prove stuff that you want, but you're able to actually prove this. So, okay, how do you decrypt? So you sort of you parse your states, you check consistency, namely you check that Z is equal, like this commitment is actually equal to the commitment of what you got on the left side. And then you output the underlying decryption. And you can show sort of because of the properties of the cryptography we put on the right-hand side, this now immediately has the write state simulatability. That's sort of easy to show. That it's still non-malleable is actually hard. You need to like go through sort of the same high-level steps to prove that the just entire non-malleable equipment scheme is secure, but you can do it. No, not at all, yeah. Really, you just need the commitment so that like this write state can break it open to get the key. Because the write sort of, again, what you have to do is use sort of, you're going to have to turn sort of functions that maul this outer code into functions which maul the inner code. And it's not so what you'd want to say is just decrypt this thing and output it, but you can't, G doesn't have the like what it needs to decrypt unless the key is hidden for him there.
Do you just commit to R0 then instead of anything like
Yeah. Okay. So, okay, again, what we've talked about is only for the synchronizing scheme. The sequential scheduling causes a few problems. Again, it's this notion that if like if your whole commitment on the left is defined by the time he gets to send his first message, he can guess what it is and then like create this bot attack. So you have to fix it. And it's not so hard. Essentially, the idea is that if the scheme is extractable, forget even extractable in this non-malleable sense, right? This scheduling doesn't require any rewind, any answering on the left. So you just make it extractable by running in parallel, sort of this very basic extractable scheme where what you're committing to, sort of the two shares, x0, x1, are actually shares of the decommitment of the scheme from before. And this will be extractable. Problems that this poses sort of are unesthetic. Like you have to repeat it many times in order to amplify soundness, which means sort of you're blowing up the complexity to deal with this like really sort of stupid man in the middle that's usually not so hard to deal with. So it's not so great. Also, you lose this bounded many non-malleability, so you have limited applications to MPC. Not so great. And so there's this new work with Vipul and with Sunu Park, and this is just like the same thing, but a better extractable component. In particular, it's sort of much better in the sense that only one repetition is necessary. So you only have to use the underlying scheme constant number of times. Also, you sort of retain these like bounded many non-malleabilities, so you have applications to MPC. And the proof is like really hard. Sort of if you want to make it so that he's not decommitting, everything breaks really horribly. So you need this like independence lemma, and you need like many new ideas to get this to go through. But yeah, I won't talk about it at all. Thank you.